Hi, my name is Matheus Machado, and advised by Roncesvalles Bassani, we formulated DyLam, a reward-weighting framework for reinforcement learning. The reward shaping technique addresses the challenge of sparse rewards, adding supplementary signals within an environment. Crafting an effective reward shape can be exhaustive. The shape defining static curriculum that the policy will learn during training. Most cases, a good shape inherits from intuitive objectives. Therefore, we can divide the major objective into make it run and control it. Finally, we have to find a set of weights to define the importance of each subtask. This final step involves training over and over again, until finding an effective set of weights to complete the task. In this work, we present DyLam, a dynamic lambda reward weighting function. By balancing multiple reward components, DyLam leads a novel dynamic curriculum framework. Our approach steers the agent's attention towards the most crucial reward component in the current context throughout the training process. As the agent's components are optimized, the method gradually reduces their weights and increases the weights of other components yet to be optimized. To integrate DyLam into any reinforcement learning method, we need to follow a few steps. The first is to acknowledge the sub-objectives and stratifying them from the original reward shape. Then, we need to range the reward components similarly. For example, in the half-sheet environment, the run component ranges from 16 to 0 per step, while the control components range from 0 to minus zero point 0.6. When normalizing these components, we are also ensuring that the weights applied are the percentage of a final sum reward. Next, we have to create value functions for each component we have stratified. The final step depends on the reinforcement learning method we want to use with DyLam. When using value-based methods like QLearning, we apply the dot product of the weights with the value functions, using it as input for a policy, like epsilon grading. When using a policy grading method, we use a similar process. This time, the output of the product will be the value which the policy wants to optimize. For DyLam's weights adjustment, we describe it with three equations. First, we want to update the performance of the agent based on the cumulative return of the last episodes. Then, we need to know how well each component is when compared with the maximum cumulative return. Finally, as we want to describe the importance of each reward with the lambda weights, we update them to sum up to 1. In this work, we validate DyLam with a discrete monolinear environment along the vanilla DeepKernel network method. The objective of this environment is to make the ship land without crashing between the two yellow flags. Felton stratifies the rewards into 4 components: power linear and angular, to be efficient, successful landing itself, and shaping, a component that sums the positional and angular distances with a signal of if the ship has landed. Compared with DyLam, we used the original environment applying the DQN and DRQ methods. DyLam shows a more simple efficient result, exposing that a static setup is not an optimal choice. We showed that DyLam focuses on balancing the spacesheet first, prioritizing the angular efficient and the shaping components. Then, it begins to look after landing. Finally, the policy is landing suboptimally, so DyLam increases the shaping component importance. In conclusion, in this work we introduced DyLam, a reinforcement learning framework that is easily integrated with any reinforcement learning method. DyLam introduces a dynamic curriculum approach, capable of doing easy subjobs first, then focusing on complex ones. We showed that in addition to being efficient, DyLam is insightful, exposing the curricula that the policies take during training. Feel free to check our implementation on the repository and read our document. Thanks for watching.